Hi, this is a video for compiler design, COMP442 and 6421. This is for week 2. In this video, I'm going to present assignment number 1. So you get the assignment from here. So the handout, this video is going to be available here. So handout is here. So there may be different versions. I found some problem here today. So I made a new version. So you get the right version by clicking on the right link here, the latest one on top. And then you get here. If you feel that depending on what kind of browser you're using, you may want to refresh your browser when you get the new version. I know this is a lame excuse, but this is what it is. Okay. So in this assignment, what you have to do is to do the lexical analyzer. So as I briefly presented in the first lecture, the introduction, which I'm going to also emphasize much more in the lecture for this week. You might have seen the video already. The lexical analyzer, what it does is basically it reads your program, which is a text file. So essentially your file is a stream of characters. What you want to do is to somehow extract the words, or in terms of terminology of compiler design, you extract the tokens from this file. So essentially the lexical analyzer, what it does, transforms a stream of characters into a stream of tokens. So that one of the things that you have to do, as explained extensively in the lecture, is you have to somehow, I'm giving you in this assignment here like a regular expression. And what you have to do is to figure out either an NDFA or a DFA, and then that will give you all the information that's necessary for, or structure necessary for implementation of your lexical analyzer. But depending on how you implement it, you might tell yourself, I don't need the DFA. However, as I will point out later, you need to provide the DFA as an additional exercise that you have something you have to provide in the assignment when you submit the assignment. Even though you might feel that you don't need it, it's a very good thing to have to make sure that you do it correctly. It's, as we will see very often in this course, if you think you can wing it or improvise in a way that you might feel is correct way to do, very often when you improvise, you end up doing things not the right way, and plus in a way that is not powerful enough or flexible enough so that it allows you to do everything. Very often when you improvise your own solution, it's going to work well for a subset of what you have to do, and then you're going to get in some cases, and then it's going to stop working. Then you're going to be tempted to add special cases to deal with the special cases for which your solution doesn't work. Then it's going to become more and more complex. That's how very often some students get in trouble in this project. And that starts with assignment number 1. So proper way to do it is to design your DFA first. Then it's going to tell you all that's necessary to understand in order to build the lexical analyzer. So here is, well, essentially what I'm doing here is that I'm giving you a regular expression, in this case, a set of regular expressions, which you have to combine into one regular expression, which you then transform into an NDFA, and then which you transform into a DFA. Now, there's many tools that are available online, automated tools that you can use. You're, of course, allowed to use them that will transform a regular expression into an NFA and then a DFA. Again, repeat, you're allowed to use these tools to do your assignment. So here is the description of what is an identifier. Very typical way of describing an identifier in a programming language is to say that it starts with a letter, and then it's followed by any number of alphanumerical characters, where alphanumerical characters are comprised of any letter or any digit or an underscore. So that's what is the definition of an identifier. Now, right away, some of you might be tempted to say, well, it looks like regular expression, so I'm going to use a regular expression feature of my favorite language, and I'm going to actually implement the lexical analyzer out of this. Again, it will work for some of the cases, but then for some other cases, which I purposefully introduced, you'll see that it's not going to work. You might be surprised that it's not going to work for everything. So even though it seems that it is a problem that you may solve using a regular expression feature of a programming language, there is limitations to that. Now, there's also numbers in this programming language. So here, define what is an integer. An integer starts with a non-zero, which is a number that is from 1 to 9, and then any number of digits which is from 0 to 9, or it is a single zero. So you see that you're not allowed to have leading zeros in a number. For example, the number 01 is not an integer. As we will see later, in this case, you have two choices, two interpretations. Either you say 01 is an invalid number, or you say 0 is a valid number, which is followed by 1, which is another valid number. Okay, I'll let you choose between the two here. Floating point number. So essentially here, this is the E notation, using the E notation. So it starts with an integer, which, as we saw, does not allow leading zeros, and then followed by a fraction. A fraction is either any number, a dot followed by any number of digits, followed by a non-zero. So you see that it does not allow trailing zeros. So for example, you're allowed to have 1.01, but you're not allowed to have 1.10. So a trailing zero at the end of your floating point number is an invalid number. Again, if you have 1.10, you might say this is an invalid floating point number, or you might say this is 1.1, which is a floating point number, followed by 0, which is an integer. Again, as we will see later, in the cases I provided, the test cases I provided, you're allowed to make a choice between which interpretation you choose. So fraction is either this here or it's .0. Okay, so that the trailing zero only is valid if it's only 0. Then you have optionally, because of course the square brackets represent optionality. So you can have the E notation to specify an exponent. So if you have an E notation at the end of a floating point number, then it starts with it starts with E, and then you have either plus or minus, and then an integer. Okay. Integer being this definition here. So that's it for the three things that require a regular expression for their definition: an identifier, an integer, and a floating point number. And what you need to do is to, because here, for example, I'm providing you with one regular expression for ID, which is defined in terms of another regular expression. Then what you must do is to incorporate each of the defining regular expressions into a single regular expression. And eventually you're going to have a huge regular expression. That is what you're going to translate into an NDFA, and then eventually as a DFA. it is going to generate a very large DFA in the end. Indeed. One of the things you can do is to actually group some of the characters together. For example, you can say digit, you can keep digit when you want to represent your DFA and submit it in your assignment. You can actually have one of the transitions, which is actually digit, because if you create one transition for each of them, then it's going to fan out every time that you actually use it, which is going to generate a very, very big DFA. So when you submit your DFA, you're allowed to group from 0 to 9 as being digit in a single transition. Of course, in your implementation, you have to be able to parse, to identify all the individual characters individually. Then next thing is the reserved words and the punctuation and the operators. So these are many of the operators that we have here. So these are relational operators. These are arithmetic operators. This is assignment operator. This is the or, and, not. These are the braces that we all use. These are the punctuation that we will use. We use also an arrow. So for those of you who wondered, there is actually kind of a significant difference between what I asked last semester and what I'm asking now. The language is going to keep the same flavor if you want, but I'm changing it every semester so that people are not tempted to reuse code of previous students. And these are all the reserved words that we will have in the language. Comments, so you're allowed to have block comments or inline comments. So that's, for example, that's exactly the same thing as what you have in C++, for example, or many other languages. What is it that you need to do? What is the work that you have to submit? First, you need to provide a document. First of all, it's important to understand that I'm not expecting you will emphasize on writing a superb document. Okay. To me, a document, what I'm asking is something that a file that contains information. No special kind of mark is going to be given as to whether how it looks or anything like that. Okay, it's just information that you need to provide in a single file. So there's 4 sections. So first section, the lexical specifications. So essentially what I'm talking about here is a rendition of what I've already explained here. Okay, so if you implement something that is slightly different from what I explained here or I've given you, then you have to give your own lexical specifications. If they are exactly the same as what I provided, then you just repeat it in your document. You have to provide a finite state automaton. So you need to generate from, first of all, as explained previously, you need to have a single regular expression for the entire specification of the language. Then you generate an NFA or NDFA out of this, and then a DFA. And then what you need to provide here in section 2 is this automaton. Even if you feel that you don't need it because you're going to do it your own way, I require that you provide this. If you don't know really how it works or how it should be done, of course, listen to the video for lexical analysis, a lecture. It's giving you the theory about this, and it's going over a single example how to do the transformation. So essentially, it's doing explaining in the video how to do Thompson's construction, and then power set construction, Thompson's construction to generate a NDFA out of regular expressions, and then power set construction in order to transform your NDFA into a DFA. Again, I repeat, there are tools online, many tools online, that allow you to do that automatically. You are allowed to use these tools. Okay, and then in section number 4, you actually, I'm asking you to list what are the tools that you are using in this assignment. So what do I mean by tools? Well, first of all, why do I ask this? Because there's one of the graduate attributes associated with this course, which is use of tools. So for example, if you are using a website to generate your NDFA and DFA out of regular expressions, then this is a tool that you use. When you do your implementation, you use a programming language. This is a tool that you use. If you use special libraries in this programming language, this is another tool that you use. Okay. You might even say if you're using certain algorithms that have been invented by someone else, such as Thomson's construction, then this is another tool that you use. Okay, so I just want you to identify what are the tools that you are using, and also to justify or explain why you are using that. So in terms of implementation, first you need to, of course, write a lexical analyzer. So in the specification that I gave above, it basically explains what are all the tokens. So let's go back here. So the tokens are ID, integer, float, and each of these here that are in the box, in the table here, in each of the cells in this table. So again, the tokens are ID, integer, float, and then each of these here are all tokens. Okay. If you want to see an example of what are the tokens or mnemonics that I give to the tokens, which is one of the things that you have to do, then you go into the files, the example files, input files that I give with the assignment in the zip file. So what is essentially the lexical analyzer? It's a function that returns a token data structure containing the information about the next token identified in the source program file. So your lexical analyzer, it's a program. It's essentially a single function that when you call this function, it actually reads from the current position in the file. It reads enough characters to identify the next token. The lexical analyzer is not a program that gets all the tokens and then puts them in a file, for example. Okay. The lexical analyzer is just a function that reads from a certain place in the file, reads enough characters to be able to identify only the next one token. Your syntactical analyzer, that's what it will use. It will only want to know what is the one next token. Okay. This is one thing that some students do. They often create a lexical analyzer that gets all the tokens and, for example, puts them in a file. And then they say, oh, I'm going to have my syntactical analyzer or my parser to read from this file. No. Okay. So your lexical analyzer, I repeat, it's a function that returns only the one next token in the file. Of course, when you submit your assignment, you can have a main function whose job will be only to repeat the calling of this function until the end of the file. Okay. So what is this token data structure? So token data structure should contain information such as the token type or a mnemonic that actually represents what kind of token that is. Okay. Again, look into the example output files that I've given in the zip file. It will tell you the mnemonics that I myself have invented or proposing. You don't have to use them, but you need to find your own mnemonics. Second, the lexeme of the token. Now, if you don't know what is a lexeme, of course, you should go to listen to the video for the for lecture number 2. Lexeme is essentially the series of characters that you read that made you identify a certain token. Okay. So you see that there's a difference between the lexeme, which is the characters that you read to find a token, which might be, for example, you find an identifier. There's in your program, there's an identifier named var, which you identify as an identifier. So your token type might be ID, whereas the lexeme is var, for example. So third thing that should be in your token data structure is the location where you actually found this token in the input file. Of course, that becomes very important for the subsequent phases of the compiler. That is where, for example, when you report errors, your compiler report errors, it will actually report the line number and possibly the character number on the line where the particular error was actually found. So this is the actual source of where the source of the error was actually found. So first, token type, second, lexeme, and third, location. Now it's possible, well, you will actually encounter lexical errors. This is again one of the things that is discussed in the video for the lecture. So please listen to the video about this. So you should produce an error token. Okay, so this is a token that you create that represents an error, which would eventually be given to your syntactical analyzer or your parser, which what it will do with it is physically discard it. I want you to generate error tokens so that when you put your tokens in a file, which I'm asking you to do, that when the marker looks at your file, actually is able to see that where the errors are located, because they appear in your token file or your error file and your error file. Okay, so error tokens. When a token is identified from a file name, for example, original file named, it should be printed into a file, original file name .out lex tokens. So for every file that you compile, you will generate a file which has the same name, which has the extension out lex tokens. If you open the out lex token file, it's a text file that contain a rendition of what are all the tokens that were found by the lexical analyzer during the compilation. So of course, it's not what a compiler does normally, but I'm asking you to do this so that we can actually see when we execute your compiler, we can actually see what is identified by your compiler, whether or not it is correct in order to do the marking. It's going to be also very useful to you when, if and when things go wrong, you can actually see what are the tokens that have been parsed up to a certain point before, for example, your program crashes. Okay. All the files that I'm asking you to generate, there's going to be quite a few over the assignments. All these files I'm asking you to generate, one or the main usefulness to them is for your own good. When you actually execute your own compiler, it will generate all of these files, and they will be very useful for you to see what actually went wrong as the program, for example, crashed or misbehaved. So that's one of the objectives of having these files, these additional output files. When lexical errors are found, error messages should be printed out in a file named original file name .out lex errors. So your lexical analyzer it should first, well, it is a function that when you call it, it returns a data structure of the token data structure as described here. But also as it finds a token, it would also, the program would output into outlex tokens, the token in question. Okay. If it finds an error, lexical error, it would also output something in the lexical errors file, the outlex errors file. So these are these three things that your program will produce as it is processing the source file. Test cases. Okay, so I'm providing you with some test cases with each assignment. So you've seen what are the input files that I proposed for assignment number 1. In this case, it was quite extensive. Okay, not to say that this is complete, but you will see that when I give you some input files for assignment number 2, clearly you will, or you might think this is very complete, but clearly, as you start thinking about it, you'll realize that there are many cases that are missing. Okay, so it's up to you to provide as many test cases that are reasonably complete. Okay, so one of the things that you'll be graded upon for each assignment is the completeness or the relevance of the test cases that you are providing. So you should try to invest some time to write yourself a good set of test cases. Okay, so it's up to you to provide your own test cases. You may reuse those that I have provided to you in the assignment handout, but in generally speaking, you should expect that they're not complete. Okay, so you should think about cases which are not included in the files that I've provided to you. Of course, you need to provide some kind of driver because your lexical analyzer, what it does, as I repeatedly said now, it's a function that when you call it, it extracts the next token, only one next token. So you should have some kind of driver. For example, that's a main function that is repeatedly calling this lexical analyzer function so that you will extract all the tokens by calling this driver. You will extract all the tokens from the input file and output all the tokens in the outlex tokens file. And if there are errors, that you will output all the errors in the program into the outlex errors file. Here are some selected examples. So as I said, especially for the leading zeros and the trailing zeros. So if you have 0, 1, 2, 3, so it's either you will identify this as this is an invalid number, 0, 1, 2, 3. Because if you look, as we said earlier, if you look at the specification, the regular expression that I gave earlier on, it explicitly excludes the fact that a number can start with leading zeros, which this one does. So it's either you will say 0, 1, 2, 3 is an invalid integer, or this is two integers, integer 0 and integer 1, 2, 3, or 123. If you have 0, 0, 1.23, then it's either it's an invalid floating point number 0.1.23, or this is an integer 0 followed by a float 1.23. So you have all kinds of combinations of these. And then you can actually have, if you have the E notation in a floating point number, as we saw after the E, what you can have is a integer. Now, as we saw here, an integer cannot have a leading 0. So E01 is actually an invalid number. So, and that's some of these cases where it gets hairy if you want to do otherwise than say this is an invalid number. Because if this here is not an invalid number, what could it be? In this case, it could be 12.34E0, which is a valid floating point number, then followed by integer 1. Even if you push it further, you could say, well, it could be 12.34, which is a valid integer number, followed by the identifier E, followed by the integer 0, followed by integer 1. Okay. Now, the more you're trying to separate this into more tokens, you will quickly realize that the more special cases here that you may want to do, the more it actually complexifies the whole thing. Okay. The simplest thing is to keep it simple and just say, this is an invalid number. Okay. Don't try to be fancy and then include all special cases and so on. It's just going to make your life more complicated than it already is. Okay. You don't need to have something fancy that includes all of these cases. Okay. What you need is a lexical analyzer that is able to extract tokens consistently for any file that you have. That's what you need. Okay. This is a valid float, valid integer, valid identifier. These are all valid identifiers, except this one here starts with underscore. If you look at the regular expression that I explained earlier, it clearly said that if there's to be an underscore in an identifier, it should be after the first character. That is the only kind of character that an identifier can start with, which is a letter. An identifier that doesn't start with a letter is somehow invalid. Okay, so then you have again the question here. I don't know, for some reason I didn't point it out here. It can also be that you will say, well, this underscore here is not valid. Then you will have ABC1. So you might say, another thing is that underscore is only a valid character if it's part of an identifier. So if you make underscore separate from one ABC, which is a valid ID, then it should actually be invalid character, which is a lexical error, and then this valid ID. If you have one ABC, you have two choices. It's either this is an invalid identifier, or this is number 1 followed by ABC. Strongly suggest that you go with this one here in this case. So one of the things you have to do is to see all these possibilities and look at what is the technique you want to use to implement your lexical analyzer, and then make a choice for each of these and make it so that you make your life as easy as possible, whether you want to choose this or this. Okay. There's no wrong answer as to which of these two choices you make. There are wrong answers, though. There would be wrong answers. For example, if you say 0, 1, 2, 3 is a valid ID, this is wrong according to the regular expressions that I gave on top. Okay. So if your lexical analyzer identifies a token which is not according to the regular expressions that I gave, then this is a mistake that there is in your lexical analyzer, which will result in marked deductions. So here are some cases. You might see in the files that there are many other cases. Maybe I could go into the files. or no, just for sake of time, I will just point out what are these different files. So there is Lex negative grading. So each of these here are files that contain special cases that are either a lexical error or special cases as noted, as I just explained. Okay. These two alternatives here, because for each of the special cases, as I just explained, there is some choices that you may make. Okay. So this gives you an output, a set of output files for each of these two alternatives that you may want to go. Okay. So that's why you have alternative 1 and alternative 2 for the negative cases. For the positive grading, this is essentially what it is. Positive grading, let's go to this one here. So positive grading, essentially it contains the list of all the things that were listed in the table in the handout, in the PDF. So when you actually read each of these here, it should actually be able to identify all of them. And these are all valid numbers, integers, all kind of valid floating point numbers, or some examples. I said all here, of course, that's not all. That's the point about testing for a programming language. It's essentially, you could have a potentially an infinite number of cases. You do have an infinite number of cases. You just have to, you know, provide as many cases that are deemed representative of as many cases as possible, right? These are all valid identifiers. This is a valid comment, valid block comment. Here you have a valid multiple line block comment, and here you have a valid imbricated block comment. Basically, that you have a block comment inside of a block comment. You will see that this is actually, if you want to do this, this is going to create some additional problems. Okay, so for example, if you are Outlex tokens. So if you call your lexical analyzer repeatedly, reading the file that I just presented, then eventually it's going to identify the equal, the plus, the or, the open parentheses, the semicolon, the if, and so on. All of those that were on the table on the top will be identified. And of course, here, this is actually representing, for example, let's say this here. This is the token not, which is represented by the lexeme exclamation mark, which was found at line 3. Okay. So as I explained in the data structure, that is the token data structure that is output by your lexical analyzer, this is somehow a textual rendition of a token data structure that I've output into my file, right? So that's it about that. So that's about it for this video. So see you in class. Bye-bye.